Hi, welcome to the 14th session on group theory. Topic of today's session will be isomorphisms between groups, and with that will be followed by homomorphisms. Probably next 2 or 3 sessions will be dealing with these concepts. Okay, I'm going to start with something funny. All right, it's unfortunately the yeah this doesn't allow me to wear some kind of like a Kamal Hassan, just change the thing. Will you recognize me? Yeah, hopefully you would, right? Let us see. Let us get started. Okay. Now suppose, let me just make sure that recording, screen share, everything is on, right? Suppose I have set, okay, which has only one single cat. Okay, since drawing this picture will be more difficult for me, okay, I'll write only cat. Okay, right. So now I want to define a binary operation on this set. On this set. Okay, so that this set becomes a group. Huh? Right? Think carefully. It's not very difficult. So what do I need? I have, okay, cat. Okay, then I should be able to add a cat. Right? I should get some element here. But then remember, there is only one element here. Therefore, how do you think I will define? Cat plus cat must again be a cat. You understand? So cat plus cat must again be a cat. So that's a binary operation. Right? Okay. The next thing I can ask is, what is the identity? There is only one element, right? So identity element, I have to say, is again a cat, because take take an element here which is cat, and take the identity element which is a cat. What is cat plus cat? Which is cat, therefore it's identity element. Then it should have an inverse. What should be the inverse? I have a cat, right? And add it to that, I get cat. This is the identity element. This is the inverse. This is the original element, right? Element. So I have made this into a group. How many of you appreciate this? Pause, review, proceed. Yeah. So now let's look at other thing. Suppose I have only the integer 0. Okay, this is my G. Only 0. This is the integer 0. The binary operation is addition. Addition. Therefore 0 plus 0 I will define it to be 0. Right? And what is the inverse? Sorry, identity element. Identity element is also 0. What is the inverse of 0? 0. Right? This is a, therefore this is a group with only one element. Right? Now let's look at the other one. This has only one. Okay. But then binary operations multiplication. Therefore 1 times 1 is 1. And what is the identity? What is the identity? That is again 1. And what is the inverse of 1? That is also 1. Right? So now notice that all these things, okay, the elements seem to be different. This is a cat, whereas this is 0, here it is 1. The binary operation is, I am just defining a binary operation here. Cat plus cat is cat, 0 plus 0 is 0, 1 times 1 is 1. Here this is the addition, this is the multiplication dot, and here it is the binary operation star. right? But are they distinct? Are they, I would not say distinct, are they different in spirit? They are not, right? So we can see all these three groups, even though the elements look different and the operations, binary operations are different, they are all the same, right? You, you follow. Instead, if you want, you can also put a single, okay? Suppose I put a star and say star, okay, star will be the thing. So let me say something like, okay, cross, cross, star cross is again cross, right? So that will be also group. So they are not distinct at all, right? So I can set up some kind of a map between these two. What is the map? F of here, okay, to this, the map is F of the cat is 0. That's it, right? Are you following? So this is a 1 1 onto map, and similarly I can map this onto this. I can also map this on one way onto this. Are you okay? Right. Now instead, let us look at again a cat, okay, and a human being, a man. This is a cat, this is a man. I want to make this into a group. I have to define a binary operation, right? If I want to make this into a group, there must be somebody who is identity. Since in the first example I made cat as a identity, let me take man to be identity. Okay, so I will declare them to be identity, right? Then what should happen to the cat? Plus the man. Since I declare this to be identity and there are only two elements here in this set, okay, if it is a binary operation, it has to be another element here. So there are two possibilities. What are the possibilities? Either this can be a man or this can be the cat. Okay, are you following? Because the binary operation, okay, when I do any two things, if you want to put a star, okay, that should be again an element. There are only two elements, therefore it could be either the man or a cat. Yes, which can it be? Yeah, are you following? See, since this is the identity, since I declared this to be identity, therefore the correct answer is this. You understand? Okay. Now let me take the cat, okay, and the cat, take the binary operation, okay, what will it be? Again, there are two options, okay. This binary operation, this should be either this element or this element. Yeah, or this element, okay. But it's a group, okay. I under this binary operation, I want to make this a group. Therefore, can this be equal to this? Then what is the inverse? So I have an element. What should be the inverse? Okay. The inverse of this, let me write simply cat. It will be difficult for me. The inverse of cat should be the identity element, the man. Okay. So there are only two choices for this inverse of element. Can it be this element? No. If this is equal to this, then what I get is a cat. I don't get identity element. Therefore, the only way I can define cat, so the only way I can define cat star cat is cat. Sorry, cat star cat is identity. Yeah, right. Therefore, the inverse of cat must be equal to cat. Notice that also on the way defined cat star plus cat equal to identity. Is it difficult? Okay, let us look at. So let me look at my man. Okay, I will map it to 1, and the cat I will map it to -1. My star will become multiplication, right? So I have this set which is man and the cat, okay, and this is the 1 and -1. So this fellow goes here and this fellow goes here, right? Now what will happen? So call this function f, then what will be f of this? This is 1. And let's look at what is man, okay, times man. That, okay, you follow that? This is nothing other than f of man because this is identity, right? This is identity by definition, but f of identity is 1, right? But this is same as f of man into f of man, because f of man is also 1, f of man is 1, the product is the binary operation is multiplication, therefore it's 1. Yeah, but what happens to the cat? So you see, f of cat is easier to write. Okay, this is equal to -1, right? Now f of cat star cat, what is that? Cat star cat we saw is identity, f of man, but that is 1. But what is f of, okay, that is equal to f of cat times f of cat, because f of cat is -1, -1, the product is 1. So what I am trying to say is, okay, this group and this group, this with the star, okay, and this group 1 plus 1 and -1 with the dot, this is also I have to write like this. This is the star, binary operation is this. Okay, so this is the set and the binary operation is star. Okay, these two, they look like different groups, but they are the same. That's what we want to capture. You wish I didn't start with this example. This is just for fun, because you wanted to think abstract. You can see finally what matters is abstract symbols and how to operate on them. That's all we meant, right? In the first example, cat star cat has to be cat. Okay. In the second example also, unfortunately, it turns out to be that. Okay. Whereas the man turns out to be identity element, right? And the cat has order 2. There's a group of order 2. Sorry, element of order 2, right? Okay. Just for fun, if you are difficulty, I will go to something much more concrete, which you have seen earlier. So I hope all of you remember one of my first example, f of a comma b as a map from R to R, where a is any R's non-zero element, b is any real number. Then f of a comma b acting on x, we will put as ax plus b. Then this collection f of a comma b, a non-zero, b in R, okay, under composition we found it's a group, right? And we also saw that f of a comma b composed f of c comma d, how does it operate? Just for fun, let me do it. That is going to be cx plus d, f of a b should act on that. This is a real number, this is d. This is going to be 8 times Cx plus D plus, yeah, B. That is ACX plus AD plus B. Okay. Therefore, this is f of alpha beta x, where alpha is AC and beta is AD plus B. Right. So we found out this. We can point the inverse, etc. Show that it's a group. We had already shown that. In that time, I also said, suppose I identify f of AB with this matrix A, B, 0, 1, okay, then this collection of such matrices A, B, 0, 1, A in R star and B in R under matrix multiplication is a group. And the composite f of, I don't remember which I wrote, yeah, f of AB, f of AB, composite f of, suppose f of AB, I send it to this matrix A, B, 0, 1, right, and f of CD, I send to the matrix CD, 0, 1, then look at the composition f of AB, composite f of CD, okay, that will be f of alpha beta. Okay, but what is alpha beta? That is A, alpha is AC, therefore that I, okay, where this alpha beta will go to alpha beta 0, 1, but that is going to be AC AD plus B and 0, 1, but that is nothing other than multiplication of AB 0, 1 and CD 0, 1. See, AC, then will be AD plus B and this. And that is nothing other than this map. The image of f of AB is this, image of f of CD is this, and f of alpha beta is this. So, if I think of this map F from this collection f of AB and to this collection ABC 0, 1, okay, and this collection with composition, and this collection, okay, with matrix multiplication, and phi of f of AB, this map is mapped into the matrix AB 0, 1. Okay, what I found was f of AB composite f of CD is phi of f of AB. This is the matrix now, right? Times matrix multiplication phi of f of CD. This is the matrix multiplication of AB 0, 1, CD 0, 1. So now come back to the beginning of my lecture. I said if I change my disguise and come and give lecture, will you be able to identify me? Right? This is what happens. Okay. Isomorph two. I am going to say two groups are isomorphic. The set and the elements may be different, and the binary operation on one group and the other group may look different, but they are essentially the same. Do you understand? Right? Let us look at one or two more examples. Okay, so I will define the now isomorphism so that you will be a little more comfortable. Okay, now you see that sometimes abstraction helps you understand better because I am looking at very concrete objects. Okay, you are really getting confused. What is happening? Yeah, I am going to give a abstract definition. With that, your understanding will become better. Now you should really appreciate why mathematics is abstract. Okay, so let us start with the definition. Let G1 and G2 be groups. Okay, a map F from G1 to G2 is an isomorphism or group isomorphism if you want. Isomorphism if one, F is a bijection, that is 1 1 and on 2, and 2, for every a x1 x2 in G1, f of x1 x2 makes sense because this is an element in G1, right? It belongs to G1, and therefore this should be at some element here. That element should be f of x1 f of x2. Notice that here the binary operation is G2. Here the binary operation is G1, right? That's all. Okay, let us do a picture and try to expand this in terms of picture. Suppose this is my G1 and this is my G2, right? This, and both are groups. Now what happens is I'm taking two elements, x1 x2, okay, and under the binary operation it is going to go to x. This x is nothing other than x1 binary operation x2 in G1, right? Now what do I know? My f of x1 must be some y1. Yeah, this must be my y1, which is f of x1, and there is a y2 which is f of x2, right? Now y1 y2 should be an element in G2, right? Now if I take f of x, that is f of x1 x2, this element, okay, gets mapped to this element, that is f of x1 x2 must be y1 y2, and of course f is a bijection. Okay, let's go back. So what we did in the first example was I have a cat and I have 1, I have 0, and this is with addition, and this is a group with multiplication, this is a group with star, okay, and all of them are isomorphic. When I say, okay, yeah, I said two groups are isomorphic, okay, there exists let me say there exists an isomorphism between any two of these three, right? Suppose you want this an isomorphism, then I will define f of 1 to 0. There is only one way I can map, right? F of 1, where will it go? It has to go to 0. Now what will be f of 1 dot 1? That will be f of 1, but that will be 0. But what is f of 1 dot 1? It should be f of 1 plus f of 1, right? In this group, f of 1 is an element here, f of 1 is an element here, therefore I should add them. But what is f of 1? 0 plus 0. What do I get? 0. So so what have you seen? So f of 1 plus 1, sorry, f of 1 dot 1 is f of 1 plus f of 1. Notice that this is the binary operation G1, this is the binary operation G2. Can you do the similar thing here? Sure. Now let's look at this element. Second, okay, what I had was a cat and a man. This is my thing, okay, and I have binary operation, right? Is that right? Now I have this one. This is the group. What are the group? 1, minus 1 and multiplication. This is a group. Okay, remember my man was the identity here, right? Then what will I do? I will map cat to minus 1. F of cat equal to minus 1, f of man equal to 1. Is it? Okay. Let us look at what is f of cat star cat. Remember, cat star cat, we already know is must be identity, right? F of identity, which is man. That is a binary operation. But I want to check whether it is equal to f of cat, okay, and dot f of cat, right? Here, this is the binary operation in this group. F of cat is what? Minus 1. And what is the binary operation? Multiplication with minus 1. Okay, that is 1. But what is f of man? Since man is identity, we send f of man to identity here 1. So it's correct. Yeah. You can you think of another group? A familiar group, very familiar group of two elements. We have used it many times. Yeah, you remember integers modulo 2 z2. What are the elements there? The equivalence class of 0 we simply denote by 0, and equivalence class of 1, that is we divide the set of integers into odd and even. Okay, or when divided by 2 the remainder is 0 or 1. Okay, then we define an addition, right? That is also two element. What is the identity there? The binary operation is 0. Therefore, it is the binary operation is addition. Therefore, the identity element is 0 there, right? And what is 1 plus 1? 0. Now, do you see? All these three groups are essentially the same. Okay. Let us get a binary map. Okay, bijection. So, let us look at Z2 under our addition, right? This consists of two elements. Okay, 0 bar. This is the equivalent class of 0 and equivalence class of 1, which is 1 bar. Okay, I will simply denote by 0 and 1, right? Therefore, I can map the bijection. So, Z2 under this addition and plus or minus 1 under multiplication, I can think of this map. F of 0 is 1 and f of 1 is minus 1. Isn't it great? Yeah. Now, this is the bijection clearly, right? Now, what happens? I have to take any two elements. Let us say 0, 0, f of 0 plus 0. This is f of 0. Okay. I have to check whether it is f of 0 plus f of 0. But f of 0 is 1. And sorry, here the binary operation here is multiplication. Therefore, f of 0 times f of 0. This is 1 and 1, that is equal to 1. But f of 0 is also 1. So, we proved this equality. Okay. Pause. Make sure you are understanding. It's long since I should have said law. I forgot. Now let us look at something else. F of 1 plus 1. F of 1 plus 1 is 0 here. But I have to check whether it is equal to f of 1 and the binary operation in this thing, that is multiplication. But what is f of 1 for me? It's a minus 1. Therefore, minus 1 times minus 1, that is plus 1. And this f of 0 is also plus 1 and so on. Therefore, f is an isomorphism of Z2 under addition to plus or minus multiplicatory group of these two elements. So let us define a word. G1, G2 are groups. Okay, we say G1 and G2 are isomorphic if there exists an isomorphism F from G1 to G2. Okay, using that language, therefore we say this group, okay, this group and this group are isomorphic, and they are also isomorphic to my cat and man group under whatever the binary operation I define. So what I want you to appreciate is the following. Okay, isomorphic groups meaning they are essentially in spirit, they are the same. There is no distinction, except the elements may look different, the binary operation may look different, but the way they behave algebraically, they are the same. Right? Again, look at my picture. On G1, I take two elements x1 and x2, and then I apply the binary operation, I get another x. Now, now on x1 goes to y1, x2 goes to y2, then I can apply the binary operation of G2 to get another y. What we claim? F of x must be y, right? Because, yeah, are you following? That is f of x1 star x2 must be equal to f of x1 star f of x2. Okay, that's our point, right? So it's essentially they are in different disguise. The telling examples are what I did. F of AB is functions, actually bijections from R to R. Very complicated object, right? R, and then you are looking at bijection, that is maps, and then composition of maps. Whereas on the other spectrum, at the other side, we have a very simple thing. R 2 by 2 matrices A, B, 0, 1, and what is the operation? Multiplication. Now we found the map which you define is a bijection, and it's also a group homomorphism. Sorry, it's an isomorphism. Okay. So let us go back. So another example. Okay. Let us look at f of AB group. Under composition to the set of matrices A, B, 0, 1, A in R star and B in R under the binary operations matrix multiplication. So what was our map? The isomorphism was phi of f of AB went to this matrix AB 0, 1. We already checked. Okay. What we checked was phi of f of AB composite f of CD is the matrix thing, f of 0, 1 and CD 0, 1. We check this equal to this. This is phi of f of AB and matrix multiplication phi of f of CD. Right. So again, oh, I forgot to screen share. I do not know. Okay, let me go back. So this, look at this group, and what are the idea? Isomorphism. The phi is an isomorphism. How do they define? Phi of f of AB is this matrix. Then we checked. Look at this. This will be f of alpha beta sum for some alpha and some beta. Therefore, phi of this is same as this. Therefore, it's an isomorphism. Right. So let me repeat again and again. Don't be psyched by symbols, etc. Right. So finally, what it matters is this. I could have actually complicated this a little more, but I don't want to do that. Okay. There is one more example which you look at. After that, I will give very easy example which always you see in algebra courses. So let us look at Z8 and let us look at the units in this. Okay, that is set of all K in Z8. So Z8 so that K is invertible under multiplication. Okay, this is a unit. What does it mean? There is an L in U of Z8, so that K times L is 1. Okay, so I hope all of you remember some integer belong to this, that integer meaning equivalence class that belong to Z8 if only K and 8 are relatively prime. Therefore, this is nothing other than 1, 3, 5 and 7, right? And multiplication. So let us look at what is 1. 1 squared is 1. What is 3 squared? 9 and hence 1. What is 5 squared? 25. 3 times 8, therefore it's again 1. 7 squared? 49. 48 plus 1, right? 6 times 8 plus 1, therefore it's 1. Correct? So this is a group U Z8 under multiplication is a group of 4 elements. And what property? All 980 elements have order 2, because 3 is not identity, but 3 squared is identity, 5 is not identity, 5 squared is identity, 7 is not identity, 7 squared is identity. Therefore, order of each of these elements is 2, right? Okay. Now let's look at, this is 1, let us call it G1. Let us look at G2. G2 consists of all these elements. The identity, permutation of 4 elements, okay? This identity elements of one of the symmetry in S4, okay? And the transposition 1, 2, the transposition 3, 4, and the cycle decomposition 1, 2, 3, 4, right? Again you can see, okay, this is the usual, okay, this is actually a subgroup of S4, okay. Again you can see 1, 2 squared is, and 3, 4 squared, these are all transposition, and this is a cycle. Yes, in last session also we saw, okay, this is the element 2, say order 2, this is also no, of order 2, LCM of this is 2, therefore this is also 2, okay. 1, 2, 3, 4, and squared is also identity, okay. Now do you see that? Now is it clear that G1 and G2 are isomorphic? Yeah. So what do you think I will do? I will take F from U of Z8 to G2. Where will I map 1 to? I will map 1 to the identity here. And where will I map 3? It does not matter where I map. It may be 2. And 5, I'll map it to 3, 4. 7, I'll map it to 1, 2, 3, 4. Yeah. And we also saw something much more interesting. If you have done all these elements, see now suppose I call the element A, okay, E is the identity, okay, that is 1 in G1, and this is identity in G2, and A equal to 3 in G1 or equal to 1, 2 in G2, and B equal to 5 in G1 and equal to 3, 4 in G2, and C equal to 7 in G1 and equal to 1, 2, 3, 4 in G2. So when we looked at U of Z8, we already saw some nice thing. Then A squared is identity, A squared equal to B squared equal to C squared equal to identity, and the product of any two elements A, B, C, AC is B and BC is A. They all commute. Okay. Then we also saw Z2 cross Z2. Right? What are the elements? 0, 0, 1, 0, 0, 1 and 1, 1. Again, you can call this as identity. This is A, this is B, this is C. So it's okay. All these groups are isomorphic. Right? Whatever I wrote as A, you identify. That's it. Okay. Suppose you want a map Z2 cross Z2 to U of Z8, okay, which is a bijection you want. Where will I map? I'll map the identity here 0, 0 to the identity here, which was 1. And I take this map 1, 0 and I call it B, therefore I will call it A there, and my A there was 3. Right? This is my A. That is, this is the A here, say sorry, identity here, this is the identity here, this is the A in this group, this is the A in this group. And B in the group was 0, 1 and this is 5, it should go to the B in this group. And C in this group was 1, 1, that went to 7. Remember 3 times 5 is what? 3 times 5 is 15. Okay, that is 1 times 8 plus 7. And 5 times 7 is 35. 35 is 4 times 8 is 32, therefore 3. So we have checked all these things. Okay, right? Therefore, we have checked. See, this kind of abstract examples they don't give. They give very easy examples. Okay, but then when you want to deal later, you should be very comfortable with this. That's why I started with the example. And if you remember, I slowly built this kind of expectation. Okay, these groups are not different in some sense. In what way? They are isomorphic. Is that clear? Okay. Now I think I should do what I said. I should do some simple examples so that you will be happy. Now let's look at additive group of R and the multiplicative group of positive reals. Right? Then given any T, okay, I want to say these are groups. I want to say they are isomorphic. Right? So the first thing you should notice is this is one thing which students don't understand. When you want to look for an isomorphism, when you want to prove isomorphism, you have to look for a map. Okay, and yeah, and usually the teacher or something is given and you verify that is an isomorphism. But in a general case, how do I construct such thing? Okay, my tip is just look for an obvious map. Given the concrete situation, there may be an obvious map. Look for that map and check whether it is 1, 1 onto or whether it satisfies f of a dot p equal to f of a dot f of b. You follow what I mean? Now let's look at in this example. I have the domain additive group of real numbers, codomain multiplicative group of positive real. Therefore, if you start with one real number, I want to end up with a positive number in the codomain. What is the obvious map you can think of? Sometimes students say x squared, okay, but remember 0 is in the domain and therefore 0 squared should also be in the codomain. That's not true. Okay, codomain consists of only positive elements, right? Therefore, what should be the obvious map? From calculus days, you know that, yeah? Exponential map, yeah? That's it. We'll go through that. So, this is e power t. Okay, now suppose I take two elements here, call this as f, what is f of s plus t? That is e power s plus t. But we know the exponential map is e power s into e power t. But that is f of s, f of t. Remember, this is the binary operation in the domain. This is the binary operation in the codomain. And is it bijection? That is clear because for each x here, my t will be log of x. Okay, and t going to ut is strictly increasing. Therefore, okay, if s is less than s is not equal to t, then either s is less than t or s is greater than t. Let us assume s is less than t, then f of s will be less than f of t. That is e power s will be less than e power t. Therefore, they cannot be equal, right? Therefore, this is a group isomorphism. Now again you see that, okay, they look very different. On the domain we have an additive notation, and the set is all real numbers. Whereas in the codomain, the second group is only positive reals, and the binary operation is multiplication. Okay, you can see they are disguises of each other. Okay, right. Okay, so let us give one more example. Let me just check. There is time. Yeah, yeah. Let us look for one more example. Okay. Now suppose let us look at G to be additive group of integers, right? G1 and G M to be all multiples of M under addition. Therefore, what is thing? This is N times M as N varies over Z. And therefore, if I take two elements, we know it's a subgroup, in particular it's a group. You understand this? Now you can see GM is strictly a proper subset of G1. Sorry, G1. So when M equal to 1, there is no problem, right? When M is not equal to plus or minus 1, let me assume my M is greater than 2, greater than equal to 2, so that I don't worry about, okay? But they are isomorphic. It looks like a very proper subset, but they are isomorphic. How many of you can see this? Suppose you start with an integer n in G1, I have to map f of n. But remember, it has to be a multiple, right? There, what should it be? Therefore, obvious thing is n times n. That will be a multiple. Now, what will be f of, let us say, r plus s? F of r plus s will, okay, what will it be? That is r plus s times n by definition. But r plus s times n by distributive law is r times n, sorry, r times m plus s times m. But r times m is same as f of r, and this is f of s, right? And is it a bijection? Yes. So f is an isomorphism. So in this example, how many isomorphisms we are given? How many of you see that? It's infinitely many, right? For every positive integer greater than or equal to 2, even equal to 1, it's identity map, okay? There are a lot of, right? Okay. So I will start with one more example, okay? Then we will take up more abstract study of group homomorphisms and isomorphisms in the next lecture. But one more easy example. Let us look at, okay, Zn under addition, okay, and nth roots of unity. Do you remember? That is e power 2 pi I by n, and okay, 0 less than equal to k less than n. There are n elements, right? Notice that both we know they are cyclic groups, right? This is generated by 1 and this is generated by e power 2 pi I by n, right? So let us call this as A. Therefore all elements of this are 0 times A, 1 times A, 2 times A and n minus 1 times A. But the same as of course 0, 1, 2, n minus 1. Are you following? Here if I call this as B, all the elements are going to be 1 when k, okay, b power 0 which is 1, b power 1 is b, b squared and b to the power n minus 1, right? So now this is a finite cyclic group under addition, whereas this is a finite cyclic group under multiplication, but both are n elements. Okay, so can you think of an obvious map? Yes, the obvious map is f of a power r goes to b power r. Now let us look at what will happen to f of r plus f of r into f of s, a power r into f of a power s. This will be f of a r plus s. Where will it go? It will go to e power 2 pi I r and e by n and e power 2 pi s by n. Okay. If you want, here I will simply say this, sorry. This is here f of r plus s. I want to check whether it goes to f of r into f of s. Right? Now remember r plus s equal to t, where t also belong to 0 to n minus 1. Right? That is r plus s. You write it as some q times n plus t, where 0 less than or equal to t less than n minus 1. That is the definition of r plus s. You understand? Yeah. Therefore, where will it go? Therefore, it should go to this is f of t. F of t will be e power 2 pi I t by n. But this will be e power 2 pi I r by n into e power 2 pi I s by n, and this by law of things we know that e power 2 pi I by s plus r by n. But if I write s plus r as q times n plus t, then this is going to be e power 2 pi I q n plus t by n. Yeah, but that is going to be e power 2 pi I q n by n, which is 1, into e power 2 pi I t, and this is 1. Okay, this is e power 2 pi I to the power q, therefore it is 1. Therefore it is e power 2 pi I t. Therefore f is an isomorphism. So what have we got is, we saw the additive group, cyclic group of n elements Zn is isomorphic to the multiplicative group of nth roots of unity. Yeah, they look very different. Yeah, again it's somewhat very different. If you really remember, my domain is there are n elements, but each n element is an equivalence class, right? Do you remember those? If I take r, what does it mean? When I divide the integers by n, all of them will have remainder r, right? It's actually an equivalence class, so different, but as groups they are the same. This is what captures isomorphism. So please go through. I know I didn't make it easy, okay, because I want people to learn much better, and so that you should become, see, I don't want to make life easy so that you get the false impression you know very well. Okay, struggle, learn, and you will be a master. Okay, hope to meet you soon. Wish you all the best.